Mainly, before we start the kinds of covalent bonds, when we can say that the bond that occurred between two atoms is a covalent bond. If we come back here to our example, we can see that hydrogen and oxygen, both of them, they are non-metals. Focus on this, guys. Non-metals. When a bond is occurring between two non-metals, we call this bond a covalent bond. So, pay attention that when a bond is occurring between two non-metals like hydrogen and oxygen, we call it a covalent bond. Now, what are the kinds of covalent bonds? Mainly we have three kinds of covalent bonds. We have the single, this is one, we have a double, this is two, and we have triple, this is three. So three kinds of covalent bonds: single, double, and triple. How can each one exist, or in which case? A single covalent bond exists when two atoms share one pair of valence electrons. One pair of valence electrons means when two unpaired electrons are shared together, okay, they form a single covalent bond. How, guys? Let's take an example. Okay. If we took hydrogen gas, H2, because as I said to you, some atoms are always diatomic. Mainly, hydrogen gas is a diatomic gas made up of two hydrogen atoms. Each hydrogen atom has only one valence electron, and it's unpaired. So if we get another hydrogen atom, also it will have only one valence electron. The first hydrogen atom has only one unpaired, the second has only one unpaired. What about if they form a bond between each other? This is the bond that can be formed between each other, and they are sharing only one pair of valence electrons. This is the first electron, the second electron. When we have two things, we call them pairs. So sharing one pair of valence electron, we call it a single covalent bond. So why single? Because they share only one pair. Why covalent? Because hydrogen atoms are non-metals. So both of them are non-metals. When two non-metallic elements share atoms together, they form covalent bond. Okay, so now we know that covalent means atoms that share electrons and they are non-metals. This is what covalent bond means, where when they share only one pair of electrons, we call them a single covalent bond. Second, a double covalent bond. When does this exist? A double covalent bond. For example, let's take oxygen gas. Now we finish with hydrogen, oxygen. We know that oxygen is in group 16. So as we said before, it has 6 valence electrons. So it's 1, 2, 3, sorry, we can't place it here at the same place, you know, so I must go to the third region, 3, 4, 5, 6. You see, guys? Now, I'll bring 2 oxygen atoms and put them facing each other. Okay. If we ask ourselves how many unpaired electrons each oxygen atom has, we can say that each oxygen atom has 2 unpaired. This is 1, this is 2, this is 1, this is 2. So every atom has 2 unpaired electrons. Okay, guys. Now, for both oxygen atoms to be stable, each one must have 8 valence electrons. So that's why they must share these electrons with other elements. So these 2 oxygen atoms will share their unpaired electrons together. They will share these 2 electrons and they will share the other 2 electrons. Now the question is, how many pairs of electrons or valence electrons are being shared between these 2 atoms? The answer is 2. This is the first and this is the second. So in this case, we have what we call a double covalent bond. Okay, so again, double because we share the number of electrons shared are 2 pairs, not 1. So it's double, and covalent because both atoms are non-metals. Okay, let's come back, or let's continue with the triple covalent bond. If you look at your periodic table, you will find that nitrogen is an element found in group 15. As we said before, an element found in group 15 has 5 valence electrons. So also, let's draw its Lewis dot structure, 2, 3, 4, 5. Okay, or we can do it in other way. If we started from here, for example, 1, 2, 3, 4, 5, or like this, 1, 2, 3, 4, 5. So just the place you start, continue the cycle and start the another one. Now, I will place 2 nitrogen atoms facing each other. 4, 5. We can do it this way. And then 1, 2, 3, 4, 5. Let's look now at the unpaired number of electrons. You can see in this nitrogen atom we have, this is the first, the second, the third. So we have 3 unpaired electrons. The same thing with the other atom, 1, 2, 3. So these are unpaired. So what will happen now? For nitrogen to become stable, it must has 8 valence electrons. So it still needs 3 more because it already has 5 and it needs 3 more. 5 plus 3 equal 8. But how can this happen? Okay. Let's get rid of these circles, and then, as we said before, for these atoms to become stable, they must share their electrons. This is 1, this is 2, this is 3. So the question is, how many pairs of valence electrons are being shared between these two atoms? We can say that it's 1, 2, 3. So 3 pairs are being shared between each other. In this case, we call this bond a triple covalent bond, as you can see here. Okay? So we call it triple covalent bond. So why triple again? Because we have 3 pairs are being shared. And why covalent? Because nitrogen atoms are also non-metals found in the yellow area or the yellow region in the periodic table, which are the region of non-metals. So in summary, guys, we have 3 kinds of covalent bond: the single, the double, the triple. Okay? In the single we share only 1 pair of valence electrons, in the double we share 2 pairs of valence electrons, while in the triple we share 3 pairs of valence electrons. These also another examples. Hydrogen and nitrogen already explained, and we have the CO2. The same thing. Carbon has 4 valence electrons, 4 unpaired. Oxygen has 2. So carbon needs 2 oxygen atoms to form the covalent bond, the double covalent bond. Okay, so what's the aim of sharing electrons? The aim, as I said before, to become stable. So when 2 or more atoms share their valence electrons, they form a stable covalent compound. Covalent compounds usually have low melting points and low boiling points. You can ask yourself, why? You remember what I explained before, that covalent compounds are made up of non-metals. And in general, non-metals have low melting point and low boiling point. They are not like metals. They are usually gases. Of course, guys. And because most of the elements which are in the yellow region, means the non-metals, most of them are gases. So that's why most of the covalent compounds are being gases or liquid at room temperature. Pay attention that I'm telling you this at room temperature. But they can also be solids, because we have some of the non-metals are solids, like sulfur, for example, and since they are made up of non-metals, of course, covalent compounds, they are poor conductors of thermal energy and electricity. So in general, these are the properties of covalent compounds, which are very similar or the same as properties of non-metals. Now, when we are speaking about a covalent bond, or a bond in general, it leads to the formation of molecules or of compounds. For example, the bonds we did here, so we can say that this is when we have the bond between oxygen and oxygen, it forms a molecule. It's O2 now. Nitrogen, it's N2 because it's made up of 2 nitrogen atoms. This is 2 oxygen atoms. So what's a molecule? It's a group of atoms held together by covalent bond. Pay attention, covalent bond. So, a molecule is a group of atoms that are held together by a covalent bond that act as an independent unit. As you can see here, that N2 is an independent unit. It's a molecule. Also, O2, H2, all of them are molecules. A molecule that has a partial positive end and a partial negative end because of unequal sharing of electron is called polar molecule. Let's focus here, guys. What do you mean by polar molecule? Now we know that a molecule is a group of atoms that are held together by covalent bond. So what do we mean now by polar molecule? Let's look here at this example. We have oxygen, the red one, and the hydrogen atoms are the blue one. As you can notice that oxygen has a negative sign while hydrogen has a positive sign here. Why, guys? A water molecule is considered polar because the shared electrons are pulled closer to the oxygen atoms. Because the electrons are pulled closer to the oxygen atom from the hydrogen atoms, then this makes it having a partial negative charge. So the electrons are being pulled closer to the oxygen from both sides. So they are giving it the negative sign. Or we can say that the oxygen atom is being a partial negative charge, having a partial negative charge. While at the same time, the hydrogen atom will have a partial positive charge. Atoms of a polar molecules share their valence electrons unequally. They share their valence electrons unequally. And you can see that, as I said before, the electrons are being pulled toward the oxygen from the hydrogen, and that's why we call it polar. While in the other examples, like in CO2, a carbon dioxide molecule is non-polar because the shared electrons are pulled equally by carbon atoms and the oxygen atoms. So when they are pulled equally, we call it non-polar. Okay. One additional idea before we continue. There is a rule related to polar and non-polar, relating mainly to dissolving. This rule says that like dissolve like. What do we mean by this? Like dissolves like. Mainly, we can say that polar dissolves polar. If a polar compound is being dissolved in another polar compound, the dissolving process took place and happens. Like, example, vinegar plus water. Non-polar dissolves non-polar. This is the same like oil plus alcohol. Okay. The question is now, when oil dissolve in water, let's answer this question together. Of course, oil will not dissolve in water. So the answer is no. Why? Why, guys? What about oil? We already explained that oil is non-polar. We can conclude it from the above examples. While water is polar. Can a polar compound dissolve in a non-polar compound? The answer is no. So this is all about polar and non-polar. We still have last part of our lesson, which is about the chemical formula. I think it's easy because we studied it before in semester 1. Let's repeat it again. What's a chemical formula? It's a group of chemical symbols and numbers that represent the elements and the number of atoms of each element that make up a compound. In general, a chemical formula describes the type of atoms in a compound or a molecule, but it doesn't explain the shape or appearance of the molecule. So, example, guys. Let's take this example into consideration. CO2. This is the chemical formula in general. So this is chemical formula. It's made up of symbols, the carbon symbol, C, the oxygen symbol, O, and numbers, which are the subscripts. Okay? When we look at this chemical formula, we know this compound is made up of carbon and hydrogen and oxygen. It's made up of one carbon atom and two oxygen atoms. So this is what a chemical formula in general. But a chemical formula itself can tell us about the shape of the molecule. So, but as we said here, it does not explain the shape or the appearance of the molecule. So what explains the shape or the appearance of the molecule is the diagram. We have learned, or we had learned till now, the dot diagram. Okay, this is the dot diagram. Or instead of using dots, we can use the lines. So every two dots is being represented by a small dash. So instead of having two dots like this, we can put a dash. It represents two dots, and we call this a structural formula. Or we can use ball and stick model, and instead of using the symbols of the atoms themselves, we use balls of different colors. As you can see here, the oxygen is being the red ball, while the carbon is the black ball, and they are attached by a stick. Okay, as you can see here and here, these are sticks, these are the balls. Okay, different balls, different colors means different atoms. So this is called the ball and stick model. And finally, we have the space filling model. We are using the same balls with different colors because of different atoms, but without sticks. So this is called space filling model, means with no space in between the atoms. So only you are required to know these type of diagrams: the dot diagram, structural formula, ball and stick model, and finally the space filling model.